On July 4th, 2012, in a seminar room in Geneva, a room packed with physicists watched a number appear on a screen. 125. 125 giga-electron volts. The mass of the Higgs boson. The room erupted. Peter Higgs, the man who had predicted this particle nearly 50 years earlier, was sitting in the audience. The last missing piece of the standard model of particle physics had been found. Decades of searching, billions of dollars, the largest machine ever built by human hands, and there it was, one number. The problem is, that number makes no sense. Not because it's wrong. The measurement is solid. The particle is real. The problem is that 125 giga-electron volts is, theoretically speaking, almost impossibly small. Understanding why takes us to what many physicists consider one of the deepest unsolved problems in fundamental science. The Higgs field fills all of space. Unlike every other field we know, it has a value even in empty space. Even in a perfect vacuum, it is switched on. Particles that interact with it acquire mass. The top quark couples strongly to it, which is one reason it is the heaviest known elementary particle. Photons do not acquire mass from it, which is why they travel at the speed of light. Neutrinos are the awkward exception. They have tiny masses, but the standard model still does not fully explain where those masses come from. And the Higgs field is not the source of all mass in the universe. Most of the mass inside protons and neutrons comes from the violent binding energy of the strong force. But without the Higgs field, electrons and quarks would not have the masses that make atoms, chemistry, and ordinary matter possible. Without it, the universe would not be structured the way it is. The Higgs boson is the ripple in that field. Smash protons together hard enough, and for an instant, you can shake the field violently enough to produce one. It lives for about 160 yoctoseconds, roughly 160 septillionths of a second, then decays into debris. You reconstruct the mass from that debris. 125 giga-electron volts. Now here is the problem. In the quantum calculations, the Higgs does not sit quietly. Its mass is affected by loops involving other particles, top quarks, W bosons, and even other Higgs bosons. Those interactions feed back into the Higgs mass, and the top quark is the killer. If the standard model is pushed all the way up toward the Planck scale, the dangerous correction is not merely too large, it is catastrophically too large. More precisely, the correction is to the Higgs mass squared. And if nothing protects it, the natural size of that correction is bigger than the measured value by roughly 30+ orders of magnitude. The Planck scale is the point where our current physics breaks. So the problem is not that the Higgs is slightly lighter than expected. The problem is that the Higgs is sitting calmly at 125 giga-electron volts when the mathematics seems to be screaming that it should have been blasted upward toward an enormous scale. Which means the theory appears to require a cancellation of almost unimaginable precision. Imagine two numbers, each more than 30 digits long. You add them, and what remains is the tiny number we actually measure. The disturbing part is that no known mechanism in the standard model explains why the cancellation should be that perfect. That is what the standard model quietly requires every time the Higgs sits at 125 giga-electron volts. Physicists call this the hierarchy problem. For 40 years, it has sat at the center of theoretical physics like a splinter nobody can remove. And then, in 2008, they turned on the LHC. The mood in theoretical physics at that moment was not cautious. It was charged with expectation. For decades, the leading solution to the hierarchy problem had been supersymmetry, a framework so mathematically powerful, so deeply embedded in particle theory, and so widely studied that many physicists expected the LHC to find evidence for it. The question was not just whether new particles would appear, it was which ones would show up first. Careers had been built on it. Graduate students had written theses mapping out the signatures these particles would leave in the detectors. The machine was built, in part, to look for them. Supersymmetry proposes that every known particle has a partner. The top quark has a stop squark. The electron has a selectron. The gluon has a gluino. And the key feature, the reason it could solve the hierarchy problem, is that the dangerous quantum corrections come in opposite directions. The top quark pulls one way, the stop squark pulls the other. In exact supersymmetry, the cancellation happens naturally. No absurd fine-tuning, no miraculous accident, just symmetry doing what symmetry does. In realistic supersymmetry, where the symmetry has to be broken, the partners cannot be too heavy. If they are, the protection weakens and the old problem comes back. It was the kind of solution that felt too good to be wrong. The LHC ran, and ran, and ran. Nothing. No stop squark, no selectron, no gluino, no clear sign of anything beyond the standard model except the Higgs itself. And a Higgs near 125 could fit some supersymmetric models, but it was not the new physics anyone needed. By the end of Run 2, the simplest search scenarios had pushed gluinos above roughly 2 tera-electron volts and stops into the TeV range. The exact limits depend on how the particles decay and how compressed the spectrum is. But the message was brutal. The light, natural superpartners that were supposed to make the Higgs problem disappear had not shown up. To keep the Higgs light with superpartners that heavy, you start needing fine-tuning again. The same fine-tuning the whole framework was designed to eliminate. 40 years of theoretical infrastructure, the dominant idea in particle physics for 2 generations, and the universe simply did not cooperate. Extra dimensions of space? Untested. A composite Higgs built from smaller constituents we have never seen? Untested. Or the possibility that disturbs physicists most, that 125 is not the output of any mechanism we can discover at accessible energies. That we live in one of a vast number of possible universes where the constants vary, and we find ourselves here because this is one of the rare places where the numbers came out compatible with matter, stars, chemistry, and life. No protective symmetry, no discovered mechanism, just the possibility that the number was selected, not derived. That last possibility, the anthropic argument, is not universally accepted. Many physicists see it less as an answer than as a retreat, but it has never been convincingly ruled out. And then there is the strangest part. With the measured Higgs mass and with the measured top quark mass, the standard model appears to sit disturbingly close to the boundary between a stable vacuum and a metastable one. The vacuum of the universe may not be the lowest possible state. It may be a long-lived state, stable enough to have lasted nearly 14 billion years, but not guaranteed by the theory to be permanent forever. And the number 125 sits right in the middle of that unease. Was that designed, derived, selected for, or just where the dice happened to fall? Nobody knows. The measurement is confirmed with extraordinary precision. The particle is real. The number is real. And every framework built to explain it has either been constrained by experiment or pushed into territory no experiment can currently reach. The Higgs boson was supposed to close the book on the standard model. Instead, it opened a chapter nobody knows how to finish. The missing particle was found, but the number it carried may be the sharpest number physics has ever had to explain. If this kind of physics makes you want to go deeper, the Higgs mechanism, the hierarchy problem, and the search for what lies beyond the standard model, we've linked a few books in the description. Thanks for watching. See you in the next one.